Hello everyone. It's a great privilege to be with Latin America tonight. I'm not going to assume that everyone is familiar with Legitimation Code Theory and the various tools. So I'm going to take you on my journey, which began with my work nearly 2 decades ago on a mechatronics engineering program in South Africa at what we call a University of Technology. I want you to imagine an engineering education environment where students were not privileged, where they had average or even poor grades for maths and science at school, where they were taught a classic silo curriculum in which the assumption was that if you simply add mathematics and science to technology and design, you suddenly got all of engineering. Now, many of these students came in with dreams of working on cars or robotics. And now imagine the shock they had when they went into the world of work for the first time. All sorts of technology and processes and human engagement that they were ill prepared for. Now, because I worked with these students from their first year and then placed them in different industries for experiential learning, I got to know many industry partners. And they all had different things to say about the engineering undergraduates in South Africa. Teach them more technology. Teach them specific kinds of software. Teach them to be more hands-on. Now, I realized in those conversations that many employers and students themselves were not taking into account the complex world of engineering practice in our 21st century. I believed they couldn't see the link between different kinds of knowledge and the practice itself. Now, at the heart of my work, I was trying to understand how engineering practitioners at different levels solved engineering problems in the real world, at the interface of science, technology, society, and nature. Now, that's the set of disciplinary spaces that engineers work in. Now, in my journey to understand engineering knowledge practices, I've used many of the LCT tools. I've used semantics to help educators link theory to practice. And in a sense, I myself have been on a cumulative knowledge-building wave, linking different social realist theories and the LCT dimensions so as to be able to understand and address the problem of engineering knowledge practice complexity. Let's return to our UNESCO definition of engineering. Engineering practitioners at all levels work at the interface of science, technology, society, and nature. Now, each of these disciplinary areas represents very different kinds of knowledge practices, very different ways of thinking. Take a moment to just think about them, and you'll see that there's something in what I'm saying. Now, when we add to this complex disciplinary and interdisciplinary space the rapidly changing world of migration, mobility, globalization, and the exponential development of all forms of technology, here we can see that the space that we're preparing our engineering graduates for is indeed extremely complex. Now, this complexity is at the heart of my work. And the question has always been, how can engineering educators enable graduates to navigate and synthesize the different knowledge practices across different disciplinary spaces in different socio-technical contexts? Now, the first really useful tool to help myself, my colleagues, and our students see the kind of complexity we're talking about in engineering was the specialization plane. Now, specialization, as many of you might know, helps to differentiate between what it is that specializes someone or something. In other words, what gives a practice or a practitioner its legitimacy. Early studies using LCT determined that different fields have different dominant orientations. STEM fields are seen as being more knowledge-focused. Art could be considered more knower-focused. Some fields don't know what they actually are. I suggest they try out this plane to figure that out. Now, the reality is that the professions require a combination of kinds of knowledge and the development of kinds of dispositions or attributes that are more than just being a certain kind of knower or having a certain kind of knowledge. Now, those early industry complaints and alumni feedback that we've gathered over the years about the soft skills gap all point to this quadrant here, the knower quadrant, as being underdeveloped. Now, I took this tool into my work with academics who were redesigning their engineering curriculum. And the interesting thing was that they themselves discovered just how much of the engineering standard is actually about the development of knower dispositions. They took what were then called exit level outcomes and are now termed graduate attributes and interpreted in various groups what the dominant orientation was. And it's interesting, you can see here how many of these lie in the knower quadrant. Now, we use the same approach, a specialization analysis, basically, to look at engineering education publications in our national and then subsequently international context. And here you can see there's a large focus on what we call the knower code. And these all have to do with more than half of what are now termed the engineering graduate attributes. Now, seeing this for themselves, those academics could set about designing strategies to develop knower dispositions. Project-based learning, for example. A well-structured project offers the opportunity to learn independently, practice managing the project ethically, engage in the various technical and social communication processes. Today, however, I'm going to move on to my particular focus, and that is the knowledge quadrant. Now, remember I mentioned that the disciplines underpinning science, nature, technology, and society are very different? Well, let's unpack these differences using the epistemic plane. When we zoom into that knowledge quadrant on the specialization plane, we get a focus on the what and how of any knowledge practice. Now, this vertical axis is about what is being addressed in any practice. The phenomenon itself, how strongly bounded it is. A strongly bounded phenomenon, like concepts like gravity and laws of motion, has what we call strong ontic relations. The thing kind of announces itself without you even having to give it words. A weakly bounded phenomenon is one which needs a context or more explanation or is ambiguous. Something like justice, for example. Now, the horizontal axis is about how we approach any phenomenon, from fixed, standardized approaches on the right-hand side to weaker, open-ended approaches on the left-hand side. Now, that axis is about the discursive relations. Now, these quadrants represent ways of thinking. Now, using this ways of thinking Cartesian plane on over 50 case studies of engineering problem solving, I looked at problem solving patterns. Now, when an engineer is approaching a technical problem, he or she needs to grasp the fundamental principles behind the problem. This kind of thinking that's necessary is what we describe as scientific or principled. In other words, the person demonstrates purest insight. Now, let's say he or she has to quantify or measure or experiment with elements of the problem. Often standardized procedural methods are required, mathematical formula or business protocols, for example. Now, these require what we call doctrinal insight. Now, the first step in problem solving, however, would probably originate in the top left quadrant, the situation itself. Now, what is the context? What are the various possibilities? Now, very often in complex contexts, it's not clear what needs to happen because either the problem hasn't been properly identified, such as in the case of where the problem solver has no insight, or what the problem is really about is not necessarily a form of knowledge and associated practice, but it's about knowers, the people in the system. Now, using this epistemic plane, I, for the PhD itself, had 12 different case studies where I interviewed engineering practitioners in situ. They also completed a form beforehand where they described a particular problem and how they went about approaching it. And I mapped the sequence of their problem-solving strategy, how they approached a problem, how they analyzed the various components, how they engaged with stakeholders to further their analysis, how they understood the identification of a particular problem, the cause of a particular problem, how they then analyzed those parts, and then how they synthesized a solution. Now, this is just one example of such a case study. And here you can see this problem solver moves across the different quadrants in a particular kind of pattern. You can also see in the top over there a kind of coding. I believe that practitioners have an orientation to problem solving. Now, this particular practitioner's orientation is quite purist. He thinks from what engineers like to call first principles. Now, the problem structure itself was a combination of fundamental principles and the procedures that were being carried out. The problem environment was very procedural, in other words, doctrinal. But there were also, that was in terms of the customer themselves, but these people who came in to help a particular customer solve a problem were situational / purist of that kind of orientation. So the point is, here you can see this little sign at the bottom says none. There's no code clash because this person was in the ideal space to be able to try and tackle this problem. Now, across all the case studies, I traced various problem-solving pathways, and there were different patterns in different kinds of industrial contexts. I looked at how the practitioner drew on mathematics, physics, and logic-based thinking in those different contexts with different kinds of knowers. I was looking not only for the insight pathways or how they were drawing on what kind of science-based physics, mathematics, and logic-based knowledge in particular contexts. I was looking for code clashes. And what I came to see was that real-world problem-solving, successful engineering practitioners are what we call code shifters. They recognize different kinds of phenomena and their respective or possible approaches in an iterative, non-linear fashion in different contexts. Now, this code shifting, moving from fixed to open-ended approaches or from strongly to weakly bounded concepts, is what defines a successful engineering problem solver. What I also discovered is that very often where the problem solver, him or herself, clashed with their environment. In other words, they had a dominant orientation, let's say, to the upper half, stronger ontic relations, but the environment was very procedural and very had complex stakeholder relations. That kind of code clash manifested as practitioners resigning from their work environments, or in fact those companies not doing particularly well. Now, one of the clear code clashes is that between higher education and industry. Now, much too much of our current engineering education is stuck in the right-hand side of the epistemic plane, fixed approaches. Why? Well, because it's much easier to assess large classes against very standardized rubrics. But all those industry complaints that we hear about all the time are about particular contexts in which engineers need to read the room. They need to be curious, humble, flexible, agile, know how to work with people. So the focus is not just on forms of science-based knowledge and the associated technologies. So how do we teach code shifting? Well, I'm going to give you a couple of examples of how we've implemented this in our context. Here, my colleague, Carl Kruger, has used this plane to design and implement a strategy to improve control systems teaching, shifting between laboratory and virtual pracs in a way to stretch students into more open-ended problem solving. He starts in the knower quadrant by drawing on their real-world experience of basic control, something like standing in a park operating a little mini drone, for example, which many of our students have. He then moves into the situational insight quadrant to elicit the range of opportunities and possible things that will determine what the principles of control are. This enables him to shift their insight into the purest principles, which they capture then as mathematical models. He pulls the mathematical models into an activity where they design and implement at a very basic level a controller in a virtual prac environment, and so on. And so he scaffolds and code shifts around the epistemic plane to build their strategy, their abilities to solve more open-ended problems within their own kind of context. Now here's another example, and this is from chemical engineering, my colleague Lydia Auret. When mapped onto the epistemic plane, what we see is that the lecturer explicitly tries to enable students to code shift from, for example, the principles of the conservation of mass and energy, to the equations themselves, to the use of software, which could be multiple types, bearing in mind the context of their specific project. And she does this in an iterative fashion. It's interesting that her previous experiments in this space were with semantics, learning how to weave the students between theory and practice in an iterative fashion over the course of her whole module that she gave. Now, here, I'm going to show you my colleague Robbie Pott, who's used the epistemic plane to build a learning experience that enables code shifting. Now, starting at the top left and moving around towards the right and then from the bottom right towards the left, we see how he describes the role of the lecturer to capture the fundamental principles, drawing on some situational threads, examples of what you might have seen in industry or what students might be aware of themselves. Now, the primary function of the lecture is to cover the purest element in whatever the course may be. These elements then get stretched into the sort of recognize and reproduce with doctrinal insight during things like tutorials, okay? Those tutorials can be stretched very practically to anchor more procedural approaches to conducting certain experiments or doing certain practicals, but they can also be pulled into the situational quadrant where you extend those practicals to refer to something else. Students can be given assignments. This is the classic problem-based or project-based learning, to draw the purest principles and doctrinal procedures into more open-ended possibilities. Different students could have different assignments or different particular contexts to draw on. The next step in this is then to move into, for example, in our case, the design phase. Our students in their final year have a capstone project, but this can be preempted even in any course before that time by issuing smaller, even group-based design projects, which require students to look more broadly at different contexts, to engage possibly with a possible customer, even if the lecturer plays the role of being that customer, to work with each other as a team, to exercise all those beautiful communication strategies, both technically and socially. So this use of the epistemic plane is all about our classroom context can be stretched to enable appropriate code shifting. We've extended this even further. It can be used to design a learner management system. Here, in this case, for example, in a different context, I used the epistemic plane to identify where and what kind of teaching, learning, and assessment opportunities are located or demand what kind of insight. And here you can see the movement from the core principles in your lecturers and in terms of what students study and the kinds of assessments, formative and summative, you can give students in this space, the kinds of assessments that are appropriate for the development of graduate attributes 5 and 6, which are about tools and forms of communication, the stretching into design and experimentation, which are graduate attributes 3 and 4 in the project or problem-based learning space. And then obviously the integrated project space, which can be developed through the use of portfolios and having project plans and developing research reports, just to extend students' graduate attribute development. We've even used the epistemic plane to decolonize the curriculum, to demonstrate how drawing on different contributors in the different fields across our African continent in this context can really enrich a student's understanding. So, for example, in the top right there, Samira Musa developed the equation to break the atoms of cheap metals, making the medical applications of nuclear technology, such as X-rays, more accessible. Ibn al-Haytham documented his use of the scientific method 700 years before Newton. Jamila Abbas in Kenya, in the Noah quadrant down below, saw that small-scale farmers were being taken advantage of based on their lack of bargaining power. So she created a simple mobile phone application to provide critical information to those farmers so that they could organize themselves and pool their resources to act as commercial farmers. This is a classic case of recognizing the knowers in the system and harnessing technologies to enable those knowers to be more powerful. So the point of using the epistemic plane in this way is not to challenge existing so-called experts, the Einsteins and Newtons in this space, but it's to enrich our students' understanding of those fundamental principles by drawing on their own contexts and examples of kinds of practices that are closer to them, whether it be culturally or geographically, that enriches their understanding as a whole. So what I hope that I've done today is to introduce you to a powerful set of tools that can help our engineering graduates and others meet the challenges of our complex world. Thank you very much. Are there any questions?